equivalent relation. Okay. Now suppose we have a set. Okay. Now we have the set. A set S has certain elements. Okay, has elements. Now we can define relations between elements. Okay. So you have a collection of objects. I think you can actually define certain relations between these objects. Okay. So for instance, let R be a relation. Be a relation between objects in a set. Let's see S. Now, if R satisfies, okay, if R satisfies Y, reflective, i.e. A RA and i.e. an element has a relation R with itself, okay, for all A in S. Now, second, symmetric, i.e. if AB has satisfied this relation, then BA also satisfies the relation. So it's symmetric. Then BRA, okay, BRA. BA also satisfies this relation. 3, transitive. i.e. if AB satisfies relation R and BC satisfies BRC, then AC also satisfies then ARC. Okay, AC satisfies the relation R. Okay, then we call R an equivalent relation. Then R is an equivalent relation. An equivalent relation. Okay. For instance, equivalent relation. Example. For instance, okay, for instance, do we have an equivalent relation? Now, equal is an equivalent relation. Equal is an, equal on relation on R. Okay, on R. Okay. Now, of course, any so you check 1, any number x equal to x. Okay. Now you see the second relation. If x equals y equal to z, then actually we can get x equal to z. So it's a sorry, this is third. So if x equals y, then we get a y equal to x. Symmetric. Now 3 is reflective. Transitive. So x equals y equals z, then we actually get x equals z. Okay. So equal is actually an equivalent relation. Now we have a lot of this example. For instance, matrices, similar matrices being similar. So R is a relation called R is so matrices. So ARB. So here R is similar. A equal to B, P inverse, that's P. Okay, so this is actually AB. A and B are similar. So P is invertible matrix. So suppose we are talking about n by n matrices. Okay, this is an equivalent relation. Okay, so matrices being similar. Okay, matrices being similar. So similar relation being similar. For matrices is an equivalent relation. You can check, okay, equivalent relation. Okay, you can check it's A is similar to A itself. A is similar to A itself. You can just choose the identity matrix. Okay, now transitive is of course transitive. A congruent to A is similar to B. A is similar to B. A is P, B, P inverse. B is, you know, C, similar to C. Let's see Q, Q inverse. Then you see A is P, replace B by Q, C, Q inverse, P inverse. So this will be PQ, C, PQ inverse. Okay. Now PQ, P times Q, this is again invertible. Okay, invertible. So this means A is similar to C. Okay, A is similar to C. Okay, so it's transitive. So being similar is actually an equivalent relation. We have a lot of this kind of equivalent relations. For instance, matrices being congruent is also an equivalent relation. Okay, you can check. It's check. You can check. For instance, the congruence to numbers modulo arithmetic is actually equivalent relation. So suppose A, you know, A congruent to B if mod n, okay, then you see A, we call this relation is an equivalent relation. You can check. This is an equivalent modulo arithmetic, or the congruent relation is an equivalent relation. You can check A congruent to A modulo n. So transitive, A congruent to B, B congruent to C modulo n. Then we actually have A congruent to C modulo n. Okay. Now it's also symmetric. A congruent to B means B congruent to A. Okay. The importance of equivalent relation is if we have an equivalent relation on a set, then we actually this relation actually determines a partition on a set S. So the next thing is equivalent. So we partition the set into equivalent sets, subsets, equivalence relation. Determines our partition on set S. Okay. So the equivalent class is we partitioned this thing into equivalent class. So for instance, equivalent class of A is defined as the set elements B in S such that B and A, B is equivalent to A, B satisfies the relation R. Suppose here R is an equivalent relation. Okay. 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 Now, so we want to prove Lagrange theorem. So let H be a subgroup. Now a subgroup is a group and also a subset of a bigger group of G, okay, of a group G, okay. Then we can define an equivalent relation. relation on G. Okay, so we see G, let's see this student blah, G1 is equivalent to G2 if only if they differ by an element by H. Okay, for some element in H, for some H in the subgroup H. Okay, so we check this relation. So one, this thing is reflective. So for instance, G1 is G1 times identity. Okay, identity, because identity does not do anything. Okay, identity times H. Now identity on H is also identity of G. Okay, identity element. So the identity of H and the identity of G, just the same thing, identity element. Okay, so this is reflective. An element is equivalent to itself. Now the second transitive. Let's see. Oh, sorry, symmetric. Okay, symmetric. So G1 and G2 satisfy this relation. Now this tells us G1 equal to G2 times some element H. Now we can, H is, a group element. The group element, we can invert that thing like a matrix. Okay, like a matrix. For matrix, we can do the matrix multiplication, do the inverse. Okay, so actually you can get G1, right, multiplication by H inverse. So you get G2 times H inverse. And then we have associative relation. So this is the G2 times H inverse. So we get a G2 times the identity element. So this is G2. Okay, you see we get G2 is G1 times H inverse. So H inverse is also in the group H. Okay, the inverse, doing inverse does not go outside the group. Okay, so you see G2 differ G1 by an element H, by a certain element in the group H. Okay, so actually we can conclude by definition G2 is satisfies this relation. G2 G1 also satisfies this relation. So it shows that it's symmetric. Now third is transitive. Okay, transitive, you see G1, suppose G1 G2 satisfy this relation. So we got a G2 is G1 okay, so this is the tells us that G1 is G2 multiplied by H. Now G3 satisfies this relation, tells us G2 is G3 multiplied by another maybe H this H1 H2. Here H1 H2, they are in the group H. Now you see we get a relation, substitute G2. Then we get a G3 times H2 times H1. Now use associative relation. Okay, then we get actually G3 H2 times H1. Now the group multiplication, H1 times H2 or H2 times H1. The group operation does is closed, i.e., two elements in this group. If you do group operation, it still lies in this group. Okay, so this H2 times H1 still lies in the group H. So you see G1 and G3 differ by an element in the group capital H. So this tells us that G1 and G3, they are equivalent. Okay, this is equivalent. Now, what does this equivalent relation actually determine? Okay, so this equivalent relation determine a partition. Okay, so the equivalent class of an element G of G is defined as the coset, coset GH. Now explicitly, GH is this set. GH is this set. Okay, so it's a G times H. Okay, here is in the capital H. Okay. Now, first of all, group multiplication. A group element is invertible. Okay, you have invertible. So if you have GH1 equal to GH2, okay. Now G is invertible. If you do the inverse thing, then you can get G inverse GH1 equal to G inverse GH2. Okay. Now G inverse cancel G, you get actually H1 equal to H2. So the two elements coincide if only if H1 equal to H2. Okay, i.e. for different H1, H2, the two elements is different. Okay, so this has the same number as element of H. Okay, the same as number of H. Okay, so you have one H, then we have an element in the corresponding coset of G. Okay, so this is the one-to-one correspondence. Okay, so this is actually a bijective. Okay, bijective. So so this GH is bijective with H. Now actually we have so for example, let me give you one example. Examples. For instance, G is a group of this 1 bar, 2 bar, 3 bar, 4 bar, 5 bar, 6 bar. So here is modulo 7. So it is a non-zero element modulo prime 7. Okay. For instance, we choose this subgroup H. So this G is a group. So the operation on the group operation, the group multiplication is the element multiplication. Okay. Okay. So for instance, 2 times 6 is 12. Now 12 modulo 7, so you get a 5 bar. Okay. Okay. So the subgroup H. Let's choose the subgroup H to be 1 bar, 2 bar. Okay. Now 2 squared, we get a 4. Okay, 2 squared, we get a 4 bar. Now 4 times 2 again, 2 cube, we get 8. 8 modulo 7, so we get a 1. So this is this is actually powers of 2. 2 power 1, 2 power 2, 2 power 3. 2 power 3 is just the 1. Okay, 8 congruent to 1 modulo 7. So H has 3 elements. Okay. Now you see 3 bar H. So we multiply everything by 3. Okay, 1, 2, 4. So you see 1 multiplied by 3, we get a 3. 2 multiplied by 3, we get a 6. Now 4 multiplied by 3, so we get a 12. Okay, 12 is 12 mod 7, so we get a 5. Okay, 5. You see, so we have now for instance, anything in the coset of 3H is equivalent to 3. Okay, for instance, 3 is equivalent to 5. Okay, because we can find an element. 3 times 4. Okay, 3 times 4 is 12. 12 mod 7 is 5. Okay, so here 4 is in H. 4 is in H. Okay, 4 is in H. So they differ by elements in H. So 3 and 5, they are equivalent. Okay, 3 is equivalent to 6. This is because 3 and 6, they differ by an element 2. Okay, and here 2 is in the group H. Okay. So you see, of course, three bar each. If you compute 6 bar each, the answer is equivalent class. So you get the same thing. Okay, you get the same thing if you compute 6 bar 1, 2, 4. Okay, if you compute it, now you get a 6 times 1, you get a 6. 6 times 2, you get a 12. 12 is 5. Okay, 6 times 24, 6 times 4, we get 24. 24 modulo 7, you get a 3. Okay, 3. Okay, subtract 21. So you see, these just rearrange the order of this set equivalent class. The same thing. So here, same. In a set, the group, the order of this group, the order of element, you can permute the order. It doesn't matter. Okay, order doesn't matter. Same set. Now, of course, if you do choose the equivalent class, 5 bar each, then you actually still get the same thing. So you get a 5 bar, 5 times 1, you get a 5, 5 times 2, you get a 10. 10 modulo 7, you get a 3. 5 times 4, we get a 20. 20 modulo, modulo 7. We subtract a multiple of 7, so multiple 2. 20 subtract 14, so we get a 6. So again, we get the same thing. The same computation. Okay, next we see the equivalent class of 3 each. Okay, equivalent class of 3 each, or 5 each, or 6 each, whatever which choice you choose. Now you see, each is 1, 2, 4. So the union of the thing, each, and 3 bar each. The coset, okay, coset. This actually gives us everything. 1, 2, 3, 4, 5, 6. Okay, so this total group G. Okay, now you see, each and they both have 3 elements. Okay, both have the same number of elements. Because they have the bijection. So actually, you see the group order of each. So we get actually each order plus 3 bar each order is actually equal to the order of G. Okay. Now this coset has the same order as each. You see, element of each plus number of element of each is actually G. So actually twice of each is the group order G. Okay, group order G. So then we get, you see, each, the number of element in each is actually a divisor. Okay, is a factor of group order. Okay, group order. So you see, in general, we have coset decomposition. So it's not necessarily we have 2 equivalent classes. You may have many equivalent classes. So coset decomposition. So we get a coset decomposition in general. So we can write G as the union. Okay, GIH, I from 1, let's see, to some number n, m. Okay, so this, let's choose n maybe. Okay, so this is actually G1H union G2H union GNH. So this equivalent sets, equivalent classes, they are pairwise distinct. Okay, pairwise distinct. The intersection is empty. They do not overlap. Okay, they do not overlap. So you see the number of element G is actually the number of the group element. Number of element in G is exactly G1H also value plus G2H number of element in there plus GNH. Now each of these things, each of equivalent class has exactly H many, okay, by the bijection. So this is H, and this is H, blah 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 blah. So this is plus H. So we actually see this is the n times a number n times the order of the group H. So you see we actually get H is actually a factor of G. Okay, so this is the Lagrange theorem. Okay, the Lagrange theorem. The order of a subgroup is a factor of the group order G. Okay. Okay. Now, given a group element, so this proves the Lagrange theorem. This proves the Lagrange theorem. Lagrange theorem. Okay. Now, given an element G, we actually have a subgroup generated by G. Okay, we have a subgroup G, subgroup H generated by G. You just do the powers of G. Okay, then the number of element of the group G is exactly the order of group G. The order of G. Okay, so we get the Lagrange theorem. The group order. Okay, so order of G, divide that thing group order. Okay, so this actually tells us the Lagrange theorem. Okay. Okay. All right, so we're done with RSA. We're done with RSA. RSA. Okay. As I mentioned earlier, RSA. Once we have quantum computer, RSA will no longer be secure because we have algorithm called Shor's algorithm. Actually, we can beat RSA. So actually, we need a quantum computer. Right now, there are other algorithms that are actually currently in practice, which is actually called, we actually use elliptic curves. Now, actually, it will be take us too far. Actually, we don't have enough material actually to talk about the elliptic curves. Okay, we don't have enough material to talk about elliptic curves. I hope in future we have a chance to talk about this elliptic curves and how do we do cryptography using elliptic curves. Okay. Okay, right now we're done with RSA and cryptography. Now, actually, we are not going to do something else. Applications of linear algebra. Okay. Today, let's do one thing. Which is actually very popular right now in machine learning. Okay. Let me talk about one paper. Okay, talk about one paper to explain the idea of machine learning. Okay, this paper. Okay, we are going to talk about this paper. Okay. Network distance based on Laplacian flows on graphs. Okay, on graphs. So this is actually one of my old paper in 2018. co-authored with some my collaborator at University Notre Dame. Okay, right now we know machine learning. Okay, machine learning is really popular, like AI. AI. In 2016, Google produced the AlphaGo that beat human Go players, Zedong Li Zedong. Okay, this is a breakthrough in computer science, machine learning. In machine learning, we have a lot of data set. Okay, for instance, we have a lot of data set. Now, how do you tell the difference of an apple with an orange? Okay, how do you distinguish an apple with an orange? So this seems really easy for our human being, but it turns out it is hard for a computer. Okay, hard for a computer. Now, for a human being, a kid or a child, like 3 or 4 years old, can easily learn the difference of a chair and a table. Okay, a chair and table. You tell a child, this is a table, this is a chair, just several times. Okay, then a child can learn what is a table, what is a chair. However, it's another story. We need a lot of data set actually to let the computer know what is a chair, what is a table. Okay, we need a huge data set actually. We need a huge data set. Large data set actually to computer learn what is chair, what is table. Now the key idea is the distance function or similarity matrices. Okay, suppose so here this is the idea. So suppose you have a lot of elements, you want to classify them. Suppose you have elements 1, object 1, 2, 3 all the way to n. Okay, some of them are tables, some of them are chairs. Okay, some of them are chairs, some of them are tables. Okay, so then what we do is we find similarity functions. Okay, similarity, Sij, all this is very often determined using certain algorithm. So this is the key. To find similarity between objects. Okay, similarity between objects. So this actually is similarity. Is a method that measures the similarity between object I and J. Between I and J. Okay. So the ideal case is if Ij they are both chair, then the similarity is 1. Okay, ideal case is similarity is 1. Okay, and it's 0. It's 0 if I and J they are one of them is chair, one of them is table. Okay, so then you get a matrix, n by n matrix. Then we get a matrix. Then we obtain a similarity matrix. Now this is the n by n matrix. Okay, n by n. Now the ideal case, you have a bunch of 1s and you have a bunch of 0s. Okay, you have a bunch of 1, you have a bunch of 0. Now suppose 13. Okay, just suppose the ideal case. Okay, suppose the ideal case. Now the ideal case, if you some parts are chairs, some parts are tables. So what you get is actually here n by n matrix. You have a bunch of 1 here. Okay, 1, 1, 1, 1, 1. You just You know, they are similar. And then here you have a bunch of y, okay, y. Okay, all others are zeros. Okay, then all others are zeros. Now this here we already classified. Okay, already classified. So the first several objects are tables, then the remaining are chairs. Okay, so this is an ideal case. Okay, we have this thing. However, we don't know the order of these elements. So some of them are chairs, some of them are tables. So somehow they are, we permute this thing. Okay, somehow they are in this order. We need to permute this thing. So in general, we need to permute this matrix. Okay, so this matrix A matrix A. Now, in general, if you rearrange the order, we don't know because we don't know by priori know the table and chair distribution. We don't know which is which. Okay, and the computer don't know which is which. Okay. Now, so here in reality, we actually have a matrix B, which differs by the matrix A by permutation matrices. Okay, so we just permuted this matrix A by some permutation matrix. P is permutation matrix. P is permutation matrix. Permutation matrix. Permutation matrix. Okay. Now you actually see okay, permutation matrix. Now you see permutation matrix does not does not change eigenvalue. Okay, does not change eigenvalue. Okay. Now we also permute the eigenvalue of A. The eigenvalue permutation does not change eigenvalue. Okay, it does not change eigenvalue. Then we use the eigenvector to do cluster analysis. So this is important now. Okay, in machine learning. So we use eigenvectors. Okay. So we use eigenvectors to classify objects. Okay. We use eigenvectors of B or A to classify object. Classify object. Okay, let the computer to decide which is table, which is chair. Okay, classify objects. Question?
Yeah, Professor, I think you shall change the page. Are you writing something?
Did I? Let's see.
Because the
okay, sorry.
Was...
Oh, I forgot to switch. Yeah, thank you. I forgot to switch. Switch to the OneNote. Sorry. Oh, my bad. Okay, my bad. Okay. Thank you so much. Okay. So actually, you see, we have n object 1, 2, 3, order n to n, and we define similarity as ij. Okay, it's similarity between I and j, object I and j. Okay. So the ideal case is similarity is 1 if ij are the same objects. Okay, like they are both tables. Okay, or they are both chairs. Okay. Now similarity is 0. Okay, if you have 3 nice similarity function. Okay, now similarity is 0 if they differ too much. Okay, one is chair, one is table. Okay, so the similarity is 0. So then we actually get the matrix A. So you have a bunch of 1. Okay, you have a bunch of 1. Now the others you get, they are not similar, so you get 0 there. So this is actually here the first. So here this is the first several objects are table, then the remaining objects are chairs. Okay, so we already classified them already. So this is ideal case. So we get the matrix A, similarity matrix. Ideal case. We already classified them. Okay. So you see the first 1, 2, 3, 4. The first 4 elements are similar. So you see 1, 1, 1, 2, 1, 3, 1, 4. 1. Okay. 1, 5 will be 0. Okay. 1, 5 will be 0. y6 will be 0, blah, 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 etc., etc. Okay, so you get a bunch of a thing, you get a bunch of ones, okay? Now you see this matrix A, you can easily find its eigenvalue and eigenvector, okay? Now, for instance, the eigenvalue, first of all, A has this eigenvector, okay? For instance, let's see A is this. Let's just make it simple, okay? Let's do y. The first three are similar. And then the remaining three objects are similar. Okay, so you have y. Okay, so you have we have six objects. Okay, the others are not similar. Okay, y5. So y4, y5, y7. So no. y5, y4, y5, y6. They are 0. Okay. 2, 4, 2, 5, 2, 6 are 0. 3, 4, 3, 5, 3, 6, they are 0. Okay. So we get this matrix. Similarity matrix. Okay. Similarity matrix. Now, this matrix, you can easily find its eigenvalue and eigenvector. Okay. So for instance, one of its eigenvector is this. y, 0, 0, 0. Okay. You check this eigenvalue 3. Eigenvalue 3. Okay, you check this matrix. Okay, you check this matrix. You will see this. This is very easy. You will see this. Okay. Now another eigenvector is this. Another eigenvector is this. 0, 0, 0, y. Okay, 0, 0, 0, y. You can multiply. You find this also eigenvector. So eigenvalue is 3. Eigenvalue equals 3. Okay, you just use definition of eigenvalue and eigenvector. Now you see what happened. We pre-assume the first three vectors, the first three objects are similar. Okay, now you see we get a very distinct feature. Okay, so in the eigenvector, the eigenvalues, the component, okay, the structure of the components tell us exactly the classification. Okay, you see? Did you see? 1, 0, 0. This tells us exactly the classification. Okay, so this is the key in when we classify object. So here is the idea. The eigenvectors tells us classification of these objects. Okay, so this is actually very important in application of classify objects. Okay, now if we permute, now we don't so lucky we get this matrix A where it's well arranged. Now in reality we get some random thing. Okay, so we need to permute A by a bunch of permutation to get arbitrary order. Okay, however, with the for instance if we permute maybe 2 with 4, so the eigenvector will be permute 2 with 4. So this will be so suppose we are permuted 2 with 4. Suppose we permute with 2 and 4. Suppose 2 switch with 4. Then the eigenvector will be this. The eigenvector will be y 0 y 1 0 0. Okay, you see. Then you can conclude it. You see y 3 4. They are actually in one cluster. They are similar. Okay, so you can classify the object in object 1 3 4 with one cluster. Okay, so you can classify the other so you get a 2 5 6 as one cluster. Okay, so this is now easy. Okay, once you get the eigenvector, you can easily find the classification. So there are some algorithm called k-means. to the average. Okay, you actually you can easily see certain distribution. Okay, see certain distribution. This is very easy to classify. Okay, use K-means algorithm to do the average. So this is the idea of how we do classification of object. Okay, so the key is try to write down similarity matrix. Okay, now how do we use similarity matrix? How do we define similarity? Okay, similarity. Now, one idea is find a reasonable distance between objects. Okay, the distance is large if they are not similar. The distance is small if they are similar. Okay, so distance function. So a key is actually define distance function. Distance function. Similar object has small distance. Unsimilar object has large distance. And then we define distance function dij. Dij, distance between object I and object G. Okay. So dij is the thing. And then we can, for instance, define maybe a good example, Sij to be, for instance, distance is non-negative. Okay. So you can define exp, negative distance. Okay, negative distance. If distance is large, okay, for instance, infinity, exp, negative infinity, so will be 0. Okay. If distance is really small, okay, d is close to 0, exp 0, so we get a 1. Okay, we get 1. So this is actually a reasonable model that we do in machine learning in cluster. Okay, in cluster. Okay, now if you have a lot of objects, okay, thousands of objects. Now it's impossible to do it by hand. Okay, to classify this by hand. Now actually we use this kind of algorithm to classify compute eigenvalue, eigenvectors. Okay. Now here for one example, let's see one example that in the paper. Okay, let's see one in the paper how this thing works. Okay, so the network distance. So suppose you have a graph. Okay. Suppose you have a graph. Now we already introduced this graph, a little bit about graph theory. Okay. Now use graph, you can mimic a lot of things. Okay. You can use graph to mimic a lot of things. Okay. So the object is a graph here. Now the entry of this graph is actually called the adjacent matrix. We talk about the adjacent matrix, which is ij equal to 1 if I and j they are connected. Aij is 0 if they are not connected. Okay, so this actually really important matrix. The idea of this paper, okay, the idea of this paper is to define a distance between certain graphs. Okay, certain graphs. So we use graphs to mimic object, and then we use graph distance between two graphs to define distance of two objects. Okay, so here the object is graph. Okay, the object is graph. Okay, so we can use. Okay, so let me explain the idea. Let's see idea. So you see, okay, so you see the three graphs. You see G1, G2, G3. Okay, we have three graphs. Okay, now you see these three graphs, they have two, community. Okay, you see they have two communities. Then graph G1 and graph G3. The two community has two bridges. Okay, now graph G1, these two communities has only one bridge. Okay. Now actually we can define similarity between these things. Okay. So the idea in this paper is we define a flow. Okay. We define a Laplacian flow. Okay. The idea is, okay, at each you see the point at each object 1, 2, 3, 4. Okay. We put a value 1. Okay. And see how the thing diffuse to other numbers. Okay. Other nodes. Okay. This is actually described by certain equation. Okay. This actually described by this equation. Let's see this equation. Okay. Let's see this equation. Okay. You see the derivative of the thing is described by certain equation. So we can write down this as a matrix equation. Matrix equation. Okay. Matrix equation. And then we learn how to solve this matrix equation. Okay. This operator L. Here, this operator L is Laplacian. It's called Laplacian. It's an important operator for a graph. Okay. And as a fact, this Laplacian is positive semi-definite. Okay. Positive semi-definite. Okay. This Laplacian is positive definite. So its eigenvalues are non-negative. Okay. Non-negative. So you see, we can solve a vector. Okay. We assign certain values to the nodes locally. Okay. And see how they diffuse over time. And so we get a vector with respect to time. Okay. Time dependent vector. Okay. And then we use this time dependent vector to see the difference between how they think diffuse differently on two graphs, to define the difference, to define the distance. Okay. So finally we get a well-defined distance. And then use this distance, we can find certain similarity matrix. Okay. Certain similarity matrix. Then we can classify objects. Okay. We can classify objects. And we, of course, we have certain effective computation scheme to compute the thing by linear algebra. Okay, so you see our simulation study. Okay, you see these three community. Actually, we can define the difference. We assume one 3 should be similar, 2 should be different. Okay, you see the picture 4. You see, you clearly see two distinct color. Okay, in green, one color in green and some part in pink. Okay, so this is our algorithm. How our algorithm actually classify objects. Okay, classify object. So you see the classification is really clear. Okay, this means this algorithm is good. Okay, we can clearly classify distinct objects. Okay, now you see what we use other algorithm. This is the other algorithm. You see what happened? The distance is so small. It's almost totally in green. Okay, almost totally in green. So the distance is so small, it can hardly tell object apart. Okay. Okay. Figure 6 is actually the eigenvectors of our matrix. And then it turns out these two eigenvectors looks very different. So we can use that thing to classify objects. Okay, we can use that thing to classify objects. You see, there are some error terms. Okay, most of them is in two color. Okay, you may see in yellow and in pink. Okay, and then there are some certain error there. Okay, so this is the idea that we explain. Okay, you see, this is our data that we classified objects. You see the classification is really clear. So we have clearly two colors. Okay, two colors. And we also have 30 things that, okay, this is figure 10 is our classification. You can see, did you see? We have 13 cluster structure, okay? We have green and other color, okay? And you see, so the cluster structure is very clear, it's really clear, okay? Now you see figure 11, okay? Figure 11 is worse, really worse, okay? Really bad. The cluster structure, we can hardly tell them apart, okay? It's a whole math, okay? You see number 12. This is what we obtained using other algorithm. So this we compare with a similar algorithm. Figure 13. Figure 13 is actually is also obtained by our data, our algorithm. So the cluster structure is weaker because the data is worse. Okay, it's data worse, but somehow it still tells us certain cluster structure using our algorithm. Okay, using our algorithm. So you see, we use the similar data, we apply different other algorithm and see 14, 15 other algorithm. You know, 14 and 15, they are actually currently widely used by many research. Okay, you see, in this situation, it behaves really bad compared with our results. You see the eigenvector. So you see the eigenvector in 16, 17. You see the structure. You see the cluster structure. You see clearly two different color. Okay, one in green and others in other colors. Okay, so you see the cluster structure. So we can classify a lot of objects together. Okay, so we can tell object apart. Okay, so this is actually really important in reality. Okay, in machine learning stuff. You see, the idea is really easy. It's just linear algebra. Okay, just linear algebra. It's not a very fancy thing. Okay. Okay. We have 30 minutes. 30 minutes. Okay, we have 30 minutes. So here is a baby example of how we actually use linear algebra. Use eigenvalue, eigenvectors to actually do something in reality, in computer science, machine learning stuff. Okay. Of course, linear algebra has a lot of applications, not just in this this area. Now we have 30 minutes. Maybe we change to another topic. Change to another topic. Let's do some part about. Let's change some topic. Okay, let me start a new book. Okay, right now, our linear algebra material is already done. Most part of our linear algebra course is already done. Our goal is for linear algebra is already achieved. Now we just do something extra, something more. Okay. Oh, let's consider this question. The remaining three lectures we will talk about certain topics in calculus 3 that is related with linear algebra, not just the calculus 3. And maybe some of you will also choose calculus 3. Maybe choose it or not. Okay, let's consider this question in. Okay, distance. We already talked about this topic already. Let's see this. let's do cross product. How we applications of cross product. Example. Okay, find the volume of parallel pipette with find the volume of the parallel pipette. With adjacent edges, PQ, PR, PS. PQ, PR, PS. Here we have the coordinate P, -2, 1, 0. And Q, 2, 3, 2. And R is given by 1, 4, -1. And S is given by 3, 6, 1. Okay. Remember, we have a formula to do the volume of parallel pipette, i.e. the cross product. Cross product. So the idea is, suppose we have PQ and PR. So we have parallelogram. And here we have PS. If you translate this parallelogram. Okay, so this is actually what we want to do. Okay, so PQ, PR, PS. So we just do a rough graph, okay? So the three vectors determines a parallel pipette. Now it's volume, So first of all, the area of the base is, you see the area of the base is PQ cross PR, okay? Cross product tells us norm product times sine. So this is actually it's norm. So this actually is PQ norm, PR norm times the sine theta. The theta is the angle between these two vectors. Okay, so this is actually exactly the area of the parallelogram. And then we dot product with, so this PQ cross PR is in the direction, vertical direction, okay? Perpendicular to PQ, perpendicular to PR. So it's a normal direction. The normal direction determined by the plane, PQR, okay? So this is normal direction. Then we take dot product with PS, okay? So actually we take dot product with PS. PS dot product with this normal direction actually gives us the height. So this gives us the volume or negative volume of this parallel pipette. So the key is to determine this thing, okay? Or you switch this notation around, okay? So or you do it by PQ. You choose different thing as base and as height, PQ, PR, PS. Okay, this also works. They at most differ by -1. Differ by a factor of -1. So the cross product we already know. Use determinant. So PQ, PR, PS. So we can use head minus tail. So we already know the coordinate of PQR. So we write down PQ, PR, PS in coordinate form. So this will be 4, 2, 2. You just believe in me, okay? 3, 3. Excuse me. 3, 3, -1. And the PS is 5, 5, 1. I think we can do this operation. This operation, dot product with cross product, we actually get this determinant. So we get a 4, 2, 2, 3, 3, -1, 5, 5, 1. Then compute the determinant. compute the determinant, so we get the volume of negative volume. Then in this case, we expand using the first rule. So get a 4, and then delete the rule and the column. So get a 3, 1, negative 5, the remaining thing. Now the second entry, so it's minus 2 times. Delete the second column, first rule. Then the remaining thing will be 3, y, negative y, 5. Okay, let me go here. Yeah. Okay, then we add 2. Then the remaining thing will be 3, 3, 5, 5. Okay, and then we finally get evaluate the determinant. Then we get 4 times 3 minus negative 5 minus 2 times 3 minus negative 5 plus 2 times 0. So we finally get this is a 4 times 8 minus 2 times 8 plus 0. So we got a 16. So the volume of this parallel pipette is actually 16. Okay, 16. Parallel pipette. Is 16. Okay. Okay, next exercise. Example. Prove that A cross B cross C is A dot C in the direction of B. Okay, and minus A dot B in the direction of C. Okay. 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 Prove. Okay. Without loss of generality, we assume C is non-zero. Assume C is non-zero. Otherwise, we just get 0 equal to 0 without log. So now, of course, if B equal to lambda of C, if B is parallel with C, then we actually get the left side B cross C will be 0. B cross C will be 0. So we get a 0 equal to, so we get the same answer. The left is 0. The right side is A times C times lambda C thing minus A times lambda C times C. This actually clearly this is 0. So we assume that B is not parallel with C. Okay. Now first of all, this is a linear in B. So we assume B is perpendicular to C. Now we can assume it suffices because we can subtract B by the projection of C. Okay. It suffices to check the case. that B dot C is 0. Because we, by linear property, by linear property, we may replace B by, B times B minus the projection of B on C, okay? So this will be C over C norm, or the projection of C, and then B dot C over C, okay? So this actually will tell us that this is the projection of B on C. If we B subtract the projection of B on C, this is perpendicular to C, okay? They think the new thing will be perpendicular to C, okay? So we assume B dot C is 0, okay? So this A cross B, remember B cross C is perpendicular to both B and C, okay? Now if we do cross product again, so this thing actually tells us that it lies in the plane determined by B and C. So this is actually, we can, by linear property, we can write as lambda B plus mu of C, okay? Lambda B plus mu of C, okay? Because it lies in a plane determined by B and C, okay? Because it's perpendicular to the plane. Okay, so here, then we use dot product. Take inner product with, take inner product with, let's see, for instance, with C. Use the fact that the BC is orthogonal. Then we get A cross B cross C, dot product with C is 0 plus mu C dot product with C. Okay. Actually, use the property of this dot product and cross product. We get negative A dot okay, B cross C dot C. Sorry, it should be this. We got this. B times C norm squared. This is the mu C norm squared. So finally, we got a mu should be divided. So we got a mu is actually negative vector A dot B. Okay. Similarly, dot product with B. Take dot product with B. Then we actually get this A cross B cross C. Dot product with B. Which is lambda B norm squared. Okay, so you actually get this. Use the property of cross product and dot product. So you got A dot B cross C cross B. Okay, and this you got A dot B norm squared C. Okay, now this you got lambda B squared. You got lambda B squared. B squared we assume is non-zero, otherwise it's trivial. Now divide by some by B squared, so you actually get A dot C is lambda. So we use the fact that the B normal squared is non-zero. Okay, so we are done. Okay, so then we are done. So finally we get this identity. Finally we get this identity. A cross B, A cross B cross C. It's linear in B. Okay, A dot C times B minus A dot B multiple of C. Okay. Okay, then you are done for this section, for this problem. Okay, problem, this problem. Find the distance of a point to a plane. Example. Find the distance of a point of the point P. Let's see. P 2, 1, 4 to the plane. Now the plane, 3 points determine a plane. The plane through point Q, Y, 0, 0, R, 0, 2, 0, and S, 0, 0, 3. Okay, we use this idea. Now those 3 points actually determine the plane, determine the, so suppose we have a plane. We have point P outside of the plane. Now suppose we have a point, let's see Q. Now this 3 point PQS, PRS. PRS determine the plane, okay? Then determine the normal direction. Then we can find the normal direction N. Then find the projection of QP onto the normal direction, okay? Find a normal vector, okay? And find the projection of P onto the normal direction, okay? So we use cross product. We use cross product. For instance, QS, QR, QS. Then use a cross product. We can determine the normal direction. Okay. So we find the vector QR and QS. QR will be head minus tail. So this will be -1, 2, 0. QS head minus tail. Okay, so this will be -1, 0, 3. So QR cross QS gives us normal direction. So we use IJK. Okay, QR is -1, 2, 0, -1, 0, 3. Find the determinant of this. So expand using first rule. So it's I times is 2, 3, 0, 0 minus G times -1, 3, -1, 0 plus K -1, 0, -1, 2. So we got this is 6 I times 6. This is G times -3. This is the K times 2. K times 2. So we got this is 6I plus 3J plus 2K. So the normal direction to this plane, the normal direction to the plane is 6, 3, 2. So let's choose N to be 6, 3, 2. Now we find the projection of PQ. Find projection of PQ on the normal direction. Okay. So first we write down the vector PQ. Okay, so the vector PQ is -1, negative y, negative 4. Maybe use p, qp. Anyway, so just negative, just give it negative. Okay, and then find the projection of PQ on N. Projection on PQ on N. So we got a projection PQ. Projection of PQ. Projection of PQ onto N. Normal direction. So what do we get is PQ dot product with N. Okay, and then we divide by the norm of N. Okay, the norm of N. So this gives us the projection of PQ on N. So PQ dot product with N. So we get this is negative 1, negative 1, negative 4 times N 6, 3, 2 divided by norm of N. 6 squared, 3 squared, 2 squared. Okay, so we get this is negative 6, negative 3, negative 8 over 36 plus 9 plus 4. Okay, so this we get 49. So this we get a negative 17. Okay, so we got this negative 17 over 7. But here the distance is positive, so we take absolute value. Okay, so distance is the positive part of the projection. So distance is the take absolute value. Okay, so we got a 17 over 7. So actually we got the distance of the point P. Distance of point P to the plane is exactly 17 over 7. Okay. Okay. Okay, now let's talk about we have 5 minutes. Let me finish using by equation of lines. Equation of lines and planes. Now, how do we determine equation of lines and equation of a plane in a certain space? Okay, the idea is the following. Now, to determine a line, we need a point on this line and also a street, a directional vector. Okay, so suppose we have a line. So suppose we have point P, which is x0, y0, z0. Of course, you can use higher dimension. It doesn't matter. Okay. Now, any point Q, x, y, z. It's possible that we may have higher dimensional thing. So we have directional vector v. Okay, v. Which let's see is this v is ABC. ABC. Okay. Now in 3-dimensional space, we need a 3 component. Now in 2-dimensional space, we need 2 numbers. Okay, 2 numbers. Now, if you normalize it, for instance, if you normalize x by 1, you actually get the slope. Okay, you get the slope. Okay. So you see, first of all, PQ. Q is on this line, means PQ is parallel to the vector v. So we got PQ should be lambda multiple of the vector v. Okay, so we get Q is x minus x0, y minus y0, z minus z0. It's possible that we have 4-dimensional space or whatever many dimensional space. Okay. Now this is lambda v, lambda ABC. So component wise, then we get x minus x0 equals lambda a, y minus y0 equals lambda b, z equals z0 minus lambda equals lambda c. Okay, it's possible that we eliminate lambda. So if we have lambda, so this is the parametric equations. Parametric equations. And then if we eliminate lambda, then divided by, so this we get x minus x0 over a equals y minus y0 over b equals z minus z0 equals c. here we assume ABC is non-zero. Okay. ABC non-zero. A, B, C are non-zero. If y of AB is 0, then actually you get you can simplify that thing easily. Okay. It's not difficult. It's not difficult. Okay. If y of AB is, if A is 0, for instance, if y of AB, ABC is 0, or two of them is 0, it's possible. For instance, lambda, for instance, A is 0, then actually we get x0 is fixed, x equals x0. Then y minus y0 over b equals z equal to 0 over c. Okay. So we get this kind of equation of a line. Okay, maybe it's good time to stop here for today. Let's continue on Tuesday. Any questions? Any questions? Okay. If you have no questions, then let me stop here and let's continue on Tuesday.